Hello everyone. We are now going to start our lecture on chapter 2.6, which is on rational functions and their graphs. Now 2.6 is the last section of chapter 2 that is in our syllabus, and that will complete our study of polynomial functions as far as chapter 2 is concerned. Now the word rational is derived from the word ratio. And ratio means that the number or the expression will appear with a numerator and a denominator, right? So it's going to appear in this form. There's going to be a numerator and a denominator. And that's how the expression is going to appear, is going to be presented. Now the numerator may or may not be a polynomial expression. However, the denominator in a rational function will always be a polynomial expression. Otherwise, it will not be a rational function. All right. We are going to discuss all the properties of a rational function, how to do some calculations on rational functions, how to come up with their domain and ranges, and then we will also learn how to draw the graphs of a rational function. Here are the topics that we are going to cover on rational functions. The first is finding the domains of rational functions. Domains means what are the x values that can be input into a rational functions. Now we have worked on this before when we were learning how to come up with domains of fractions. All right, so this should be somewhat familiar to you, but we are going to go into more details and also learn how to express the domain for the rational functions. We use the arrow notation. So this is something new that we will learn. Identifying the vertical and the horizontal asymptotes. Asymptotes are lines along which a graph runs but does not quite touch the line. All right. So we will discuss this further in this section. Then using transformations to graph rational functions. So we will have the basic rational function, which by the way is 1 divided by x. So f of x, a rational function, appears in this form. The basic rational function 1 divided by x. Just like we had a basic function for quadratic functions, it was x squared. For absolute value functions, it was absolute value of x, and so on. For rational functions, the basic function is 1 divided by x. We are going to then go into graphing rational functions, identifying slant asymptotes, and then solving applied problems, some application problems involving rational functions. Now, what is a rational function? As I said before, rational functions come from the word ratio, so it is expressed in ratio form with a numerator and a denominator. So this function f of x here is written as p of x divided by q of x, where p and q are polynomial functions and q of x, which is the denominator, cannot be a zero because that would mean division by zero, and division by zero is always undefined. All right, it does not give us a real number for an answer, right? It is an undefined value. Now the domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So when we go to find our domain, it says here q of x can never be a 0. So we have to exclude those values of x from the function, from the input to the function, which will make the denominator equal to 0. And we've talked about this in a previous chapter as well. All right, but we will now go into more complex rational functions and learn how to know or how to find the values of x from a given higher order polynomial rational function, higher order rational function, which will make the denominator equal to 0. Here's an example on finding the domain of a rational function. So the question is, find the domain of the rational function f of x equals x squared minus 25 divided by x minus 5. So whenever it's a rational function, whenever the expression has a denominator in it and there is an x variable in the denominator, we have to make sure that we do not input any values of x or any values of the variable which will make the denominator equal to 0. So we have to identify that value, and then when we write out the domain, we have to make sure that that particular value is excluded from the domain. So the solution here says rational functions contain division. Because division by 0 is undefined, we must exclude from the domain of each function values of x that cause the polynomial function in the denominator to be 0. So when we find the value to exclude, just focus on the denominator. You do not have to worry about the numerator, because the numerator, uh, even if it is 0, doesn't affect or doesn't cause any problems, because 0 divided by any number is 0, which is a real number. However, division by 0 is what would cause a problem. So we just work with the expression in the denominator, in this case x minus 5, make it equal to 0 and solve for x. That means what value of x uh, would make x minus 5 equal to 0. So we just solve for x. This is a very simple equation. X minus 5 equal to 0. Move the minus 5 to the other side, so x equals positive 5. So the domain of f consists of all real numbers except 5. All right. So we can include any value from negative infinity to positive infinity into the domain of this function, but we cannot allow 5 to be included in the domain. So the way we write this in interval notation is this way. We start with minus infinity, and then we go all the way up to the number 5 and surround it with a round bracket, not a square bracket. A round bracket tells us that 5 is not included in the domain. You can go as close to 5 as you can from the negative side, but it cannot be a 5. And then after we exclude the 5, after we cross the 5 in our number line, we can include any value as close to 5 on the right hand side as possible. So again, round bracket, because that will tell us that 5 is not included in the domain, and then 5 comma positive infinity. All right, so that's how we write the domain once we find the value to exclude from the domain. Now there are two ways of expressing the domain. There are two types of notations. One is called the set builder notation and the other one is the interval notation. Now the interval notation is what we have learned so far, which is in the previous slide. This is how I wrote out the domain with a round bracket, then minus infinity comma 5 round bracket, closing, then union sign, and then again round bracket 5 comma infinity round bracket closed. All right, so you're probably familiar with the interval notation, which is this one here. The other one is set notation. So this is the one, the first one here is the set notation, and the way we uh, write the domain in set notation is start with a curly bracket and then write your variable, the domain variable, which is x, and then a vertical bar reads like this, x such that. All right, so this vertical bar reads as such that. Let me write that down here, such that. All right, that's what this vertical bar reads, x such that x is not equal to 5 and close the brackets. All right, that means we include x can be any value but not equal to 5, right? Here's another example of finding the domain of a rational function with a different function here. It says g of x equals x divided by x squared minus 25. So here we have a quadratic expression x squared minus 25, and we have to find the domain of this function. Now, again, rational functions contain, because there's a division involved here, we have to make sure that we do not include any values of x which will make x squared minus 25 equal to 0. So all we do is take just the denominator, x squared minus 25, make it equal to 0 and solve for x. Find the value of x which will make x squared minus 25 equal to 0. So they have used the square root method. They have first moved the minus 25 over to the other side so that we just have x squared equals 25. And then they've taken the square root. All right, they've taken the square root of both the sides, plus minus, and come up with the two values of x, plus and minus 5. So the domain would consist all real numbers except negative 5 or positive 5. Now we could have solved this x squared minus 25 using the sum of or rather using the difference of squares formula as well. We have x squared, and let me just show that here. We have x squared minus 25 equal to 0. Now x squared minus 25 is difference of squares. Now when it's difference of squares, it has a formula. It's a plus b times a minus b, correct? So we can write it as x plus 5 times x minus 5. That's the difference of squares equal to 0. Then make each factor equal to 0 and solve for x. X equals negative 5, and then take the second factor, which is x minus 5, make it equal to 0, and you'll get x equals positive 5, and you get the same solution, but you can use the square root method as well, the way they have done here, but I just wanted to show you the other method as well. So how do we express the domain when we have two values to exclude? Again, they've used both the set builder notation and the interval notation. So in the set builder notation, we start off with with curly brackets, parenthesis, and then write your input variable, your domain variable, which is x, put a vertical bar which reads such that, so x such that x is not equal to negative 5, comma, x is not equal to 5. So which means you can include anything into the domain except x equal to negative 5 and x equals positive 5. In the interval notation, you start from negative infinity. So we start with a round bracket and then negative infinity, comma, we go all the way up to -5, as close as we can to -5, but we cannot include -5. We have to exclude that -5 value. So use round bracket, which means exclusion, and then union symbol. Now we can start immediately after -5 and go all the way up to +5, as close as we can to +5, but exclude +5, and therefore the round bracket to close it, and then again union, and then immediately after 5 we can start inputting any value of x all the way to +infinity. Now, one last example on finding the domain of rational functions. This particular function h of x equals x plus 5 divided by x squared plus 25 is a little bit tricky, as well as its domain. All right. So we have here in the denominator x squared plus 25, and we have to make sure that x does not end up taking a value that will make x squared plus 25 equal to 0. So we start the same process of taking the expression in the denominator, making it equal to 0, and solving for x. So after solving for x, so they moved plus 25 over to the other side, which made it minus 25, and they ended up taking the square root of both sides, but we are ending up taking the square root of a negative value, right? We are taking the square root of a negative value, and we cannot take even roots of negative values. It does not give us a real number, it gives us imaginary numbers. So after simplifying plus minus square root over -25, the solutions for x are plus minus 5i. Now, let me quickly explain on the side how they simplified square root over -25 and came up with plus minus 5i. So the way to go about that is we have square root over -25. So we split that and write it as square root over 25 times square root over -1. Okay, so we rewrite -25 as 25 times -1, the factors of -25. And when we do that, we can distribute the square root sign to both the factors. So we have square root over 25 times square root over -1. Square root over -1 is represented by I, and square root over 25 is plus minus 5. So our simplified solution is plus minus 5i, and that is how they came up with this answer. All right, with this answer. Now, it's an imaginary value. Okay, so what does that mean as far as domain is concerned? That means there is no value of x which will make the denominator equal to 0. That's the conclusion. All right, so when you get imaginary values as solutions of x, the conclusion is that we can include any value of x starting from -infinity to +infinity, because there is no real value of x which will ever make x squared plus 25 equal to 0. And that's what they've written here. No real numbers cause the denominator of h of x to equal 0. The domain of h consists of all real numbers, so we just write it as domain is -infinity, comma infinity. So again, when we have imaginary numbers as solutions of x after equating the denominator to 0, then the conclusion is that There is no such value which will make the denominator equal to 0. So the domain is open from negative infinity to positive infinity. Now let's talk about vertical asymptotes of rational functions. So the definition given here is the line x equals a is a vertical asymptote of the graph of a function f if f of x increases without bound as x approaches a. So let me explain that using these graphs here. All right. So we see a dashed vertical line in both the graphs, correct? Now that this vertical lines on a coordinate plane will cross the x-axis at a 90-degree angle. All right, and their equation is written as x equals a. So we have vertical lines crossing the x-axis at particular points. All right, and therefore the line is going to have an equation x equals a. Now we see over here that this graph, all right, the graph here is approaching the line x equals a, this vertical dashed line. It's approaching from the right hand side, and as it approaches the vertical line, it rises without bound. That means this graph is heading towards positive infinity unrestrained. However, the graph will never touch the vertical line, or it will never cross it, but it will get as close as possible to the vertical line as it is rising, but it will not quite touch it. All right, and that's what makes it an asymptote. So it is a line along which the graph of the function rises without bounds. It goes all the way to positive infinity. Here, when it rises up, that means it's heading towards positive infinity. Now, the way we express this behavior of the graph is start with as x and then an arrow. All right, an arrow, and then a is the line. All right, so as x approaches a, and then you see here a positive sign put here as a superscript, right? So which means it reads as x approaches a from the positive side of the x-axis, the function f of x approaches positive infinity. So let me write that here, the same thing. Let me write it out. So we write as x approaches. So this arrow reads approaches as x approaches a from the positive side. All right. So here you see we are moving towards the line, towards the vertical line from the positive side. All right. And then we just say comma f of x equals, not equals, we just say f of x approaches infinity. For the second graph here, we see that the vertical line, it's the same line, x equals a, but the graph is approaching the vertical line from the negative side. Okay, so as the graph approaches the vertical line from the negative side, it rises without bounds. It is approaching infinity. Again, it will never touch the asymptote, or it will never cross it, but it's going to get as close as possible to the line and go up to positive infinity. So The way they have represented that is as x approaches a from the negative side, f of x approaches positive infinity. So whenever a graph rises up, that means it's heading towards positive infinity. Now in the previous slide, we saw that the vertical asymptote had a graph that was rising along the asymptote to positive infinity. In this slide, they have presented a different scenario where the graph falls. The function decreases, that means the graph falls unbounded on the negative side towards negative infinity. All right. So let's read this. It says the line x equals a. So it's the same line, vertical line, crossing the x-axis at a, is a vertical asymptote of the graph of a function f if f of x decreases without bound as x approaches a. So we have the same vertical line, but we have this graph which, instead of rising as in the previous slide, instead of rising, it's falling towards the negative side unbounded, but along the vertical asymptote. And the way they have expressed that behavior is as x approaches, this arrow means approaches a from the positive side. So this graph is going towards a from the positive side. The f of x, the function, approaches negative infinity. Likewise, over here in this graph, the graph is approaching the asymptote from the left-hand side and it's falling unbounded towards negative infinity. Only difference between the two is one is approaching the asymptote from the positive side, and in the second graph, the graph is approaching the asymptote from the negative side, and the function is heading towards negative infinity in both cases here. Now we will discuss where the vertical asymptotes of a rational function are located. It says here if f of x equals p of x over q of x is a rational function in which p of x and q of x have no common factors and a is a zero of q of x, the denominator, then x equals a is a vertical asymptote of the graph of f. So in simple terms, what this says is we will have a rational function which has a polynomial expression in the numerator and a polynomial expression in the denominator. Q of x is the polynomial in the denominator. The first thing we must make sure is that there are no common factors between p of x and q of x. So we may need to factor out the numerator and the denominator and make sure there are no common factors in the numerator and the denominator. All right? In the numerator and the denominator. If that is the case, then we will need to solve for x in the denominator. So it says here a is a zero of q of x. Now in order to find what is the zero of q of x, we need to make q of x, whatever that expression is, equal to 0 and solve for x. We solve for x, okay, and we will find that those values of x are where the vertical asymptotes are located. So it'll be easier to follow if we work through an example. So that's what we are going to do in the next slide. But these are the steps we are going to take in order to locate the vertical asymptotes. First, we will need to factor. If it is factorable, then we'll need to factor p of x, the numerator and the denominator. Once we do that, we have to identify if there are any common factors between the two. And if there aren't any common factors, then we just take the denominator, make it equal to 0, and solve for x. And whatever value we come up for x, those are going to be the vertical asymptotes of the rational function. Let's go through this example of finding the vertical asymptotes. The function given to us is f of x equals x divided by x squared minus 1. So what is the first step we must do? We have to make sure that there are no common factors between the numerator and the denominator. Now we cannot factor the numerator, it's only x. For the denominator, yes, we can factor x squared minus 1 and write it as x plus 1 and x minus 1, because x squared minus 1 is the difference of squares, right? Excuse me, let me just erase the plus and make this a minus. Minus 1 minus 1. All right. And we see that there are no common factors between what we have in the numerator and the two factors of the denominator, correct? So since there are no common factors, the next step is to take just the denominator expression, q of x, the denominator expression, in this case it's x squared minus 1, and solve for x. So essentially what we are doing is we are taking, as part of step 2, we are taking x squared minus 1, make it equal to 0, solve for x. You can use the square root method, or you can use, over here we've already factored it, so we can write it as x plus 1 times x minus 1 equal to 0, make each factor equal to 0, and get a value of x. All right. So here we'll have x equals negative 1, and when we equate the other factor, x minus 1 equal to 0, then we get a value of x equals positive 1, and these two numbers, negative 1 and positive 1, are where the vertical asymptotes of the rational function are going to be. Now keep in mind, when they say the zeros, it's not the zeros of the rational function. It's the zeros of just the denominator. So we just take the denominator and make it equal to 0 and solve for x. We are not finding the zeros of the entire function. If we did, we would have to take this entire function, x divided by x squared minus 1, make it equal to 0 and solve for x. But that's not what we need to do here to find the vertical asymptotes. All we need to do is just take the denominator expression, make it equal to 0, and solve for x, and that'll give us the vertical asymptotes for the graph of f. Now let's plot the vertical asymptotes we found previously on the graph here. All right. We saw that the vertical asymptotes would be located at x equals negative 1 and x equals positive 1. How did we do that? We took the denominator of the rational function, made it equal to 0, and solved for x. When we did that, we came up with x equals negative 1 and x equals positive 1. They are also the zeros of the denominator and just the denominator and not the entire rational function. All right. So we have shown here the asymptotes using dashed lines passing through x equals -1 and x equals +1. And we see that these two lines have divided the plane into three sections. There's a left-hand section, there's a middle section, and there's a right-hand section, right? And so the graph is broken up into three parts here. The left-hand graph, we see it drops to negative infinity, correct? This graph is decreasing unbounded. The graph is dropping unrestrained all the way to negative infinity along the line x equals -1, this asymptote. The graph in the middle rises along the line x equal to -1 all the way to infinity. The same graph drops to negative infinity along the line x equals +1, all right? X equals +1. And the graph on the right-hand side, we see as it approaches x equals +1, it rises to infinity without bounds, all right? Here is example 2 showing a different case of finding the vertical asymptote. So the function given to us is h of x equals x minus 1 divided by x squared plus 1. So x minus 1 cannot be factored because first we have to identify whether there are any common factors between the numerator and the denominator. X minus 1 cannot be factored further. X squared plus 1 is not factorable either. All right. So that immediately tells us that there are no common factors. We can take our denominator expression, make it equal to 0 and solve for x to find the vertical asymptote. So the denominator is x squared plus 1 equal to 0, right? We move the plus 1 over to the other side and it becomes x squared equals -1. And then we take the square root of both the sides. Okay, and then we see that we have ended up taking the square root of a negative value, and therefore the answer of x is plus minus I. It's an imaginary value. So because there are no real solutions of x, therefore this function will not have a vertical asymptote. The domain will be any value from negative infinity to positive infinity. It does not have a vertical asymptote. That's a conclusion when we come up with an imaginary solution for x. So it says here we cannot factor the denominator of h of x over the real numbers. We cannot factor it, but we've solved it and we found that the solutions are imaginary. Therefore, the denominator has no real zeros. Thus, the graph h has no vertical function. And when we see from this graph that it's pretty much a continuous graph. All right. Now we'll define what a horizontal asymptote is. So far we talked about the vertical asymptote, which run vertically and have the equation x equals a. A rational function could have horizontal asymptotes as well. Those are horizontal lines with the equation y equals b, because horizontal line cross the y-axis. So the line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. So what we see in these three separate graphs is that we have the graph approaching the horizontal line. It approaches the horizontal line as it goes further and further to the right. As x values increase, it's heading towards y equals b, towards this dashed line. It will never touch that line, but it'll get as close as it can to that line. All right, so the way we express it is as x approaches infinity. So this is a different way of expressing the behavior than we did for vertical asymptotes. For the horizontal asymptotes, we write it like this: as x approaches infinity, as we are moving along the x-axis further and further to the right for increasing values of x. As x approaches infinity, f of x, the y value, approaches b. It gets closer and closer to the line of y equals b. It approaches b, okay? It is not equal to b. It approaches b, and therefore this arrow notation. Let's look at the second graph here. The same thing, as x approaches infinity, as we move along the x-axis towards the right for increasing values of x, f of x approaches b from the upper side, from the upper end of this line of the horizontal asymptote. And finally here, we see as x approaches infinity, f of x approaches b. Now we see that this third graph here, it does cross the horizontal asymptote, but after a certain point, as x increases, as we go towards the increasing values of x, the graph on the right end is approaching y equals b. We are now going to learn how to locate the horizontal asymptotes of a rational function. The process is different from that of finding the vertical asymptotes. It follows some rules. So we'll go through what the rules are first and then apply them on an example. So it says here, let f be the rational function given by f of x equals a rational function which has a polynomial expression in the numerator and a polynomial expression in the denominator, where a sub n is the leading coefficient of the numerator, is not equal to 0, and the leading coefficient of the denominator, which is b sub n, is not equal to 0. Then the degree of the numerator is n and the degree of the denominator is m. What this means is, in order to find the horizontal asymptotes, we need to make a note of the degree of the polynomial in the numerator and also that of the denominator. What does degree mean? Degree means the exponent of the leading term. Exponent of the leading term of the numerator is denoted by n, and the exponent of the leading term in the denominator is expressed as m, is defined as m. So we have to take into account the exponents of the leading term only, n and m, and then we apply these rules. If n is less than m, if the exponent in the numerator is less than that of the denominator, then y equals 0 is the horizontal asymptote of the graph of f. Y equal to 0 is essentially the x-axis. So that means the x-axis is the horizontal asymptote of the graph if n is less than m. If n equals m, that is, if the exponents of the leading terms in the numerator and denominator are the same, then the line y equals a sub n divided by b sub m is the horizontal asymptote of the graph. What is a sub n and b sub m? These are the coefficients of the leading term. So the ratio of the leading of the coefficients of the leading term would make up the horizontal asymptote. And then finally, if n is greater than m, the graph of f has no horizontal asymptote. So let's say we have here an example, as an example, 4x divided by 2x squared plus 1. 2x squared plus 1, and we want to know if this would have a horizontal asymptote. If it does, where this would be located. So we first note the exponent of the leading term. There's only one term in the numerator, correct? There's only one term in the numerator and its exponent is 1. So n is going to be 1 in this case. N equals 1. And in the denominator, which we denote by the letter m, the exponent is 2. The leading term is 2x squared. The exponent is 2. So m equals 2. Now we compare n and m. Is n less than m? Yes, 1 is less than 2. Therefore, we apply this rule here. The horizontal asymptote is going to be the x-axis, or y equals 0. All right, so in this case, it's going to be y equal to 0, which is essentially the x-axis. That's our horizontal asymptote. Let's take another example, which is, let's say we had, instead of 4x divided by 2x squared plus 1, we have 4x cubed minus 1 divided by 2x squared plus 1. Okay, so again, the same process. We start by looking at the exponents of the leading term. In the numerator, n is equal to 3, which is the exponent of the leading term, and m, sorry, this was 1, m, which is the exponent in the denominator, equals 2. All right, now we compare n and m. Is n greater than m? Yes, right? In this case, n is 3 and m is 2. 3 is greater than 2. So the horizontal asymptote will be none. There's no horizontal asymptote because rule 3 applies. If n is greater than m, the graph of f has no horizontal asymptote. And then finally, let's come up with another example where we have 3x squared plus 2 over 6x squared plus 1. All right. What happens here? N equals 2. M also in the denominator, the leading exponent is also 2. Both are equal to each other. N equals M. Therefore, the conclusion is the horizontal asymptote is going to be the ratio of the leading coefficient. So 3 over 6, 1/2, right? So the horizontal asymptote is going to be y equals 3 over 6 or 1/2 if we reduce it, right? So it's going to be the horizontal line passing through y equals 1/2. Let's go through this example here. It says find the horizontal asymptote if any of the graph of the rational function. Again, the function here is 9x squared divided by 3x squared plus 1. We start by looking at the exponents of the leading terms in the numerator and denominator. The leading term in the numerator is 9x squared. There's only one term in this expression in the numerator. So n is going to be equal to 2. Let's look at the leading term or the leading exponent in the denominator. And here too, we see that m equals 2. So now compare n and m. All right, n is equal to m. Both are 2. Therefore, the horizontal asymptote is going to be the ratio of the coefficients. The ratio of the coefficients of the leading terms. So 9 divided by 3. All right, so the horizontal asymptote is going to be 9 divided by 3. When simplified, it's going to be 3. So the horizontal asymptote is going to be at y equals 9 divided by 3. So we express the horizontal asymptote as an equation in equation form. So it's going to be at y equals 3 is how you're going to write it. Let's just read through the solution. It says the degree of the numerator is 2, is equal to the degree of the denominator, which is also 2. The leading coefficients of the numerator and the denominator, 9 and 3, are used to obtain the equation of the horizontal asymptote. The equation of the horizontal asymptote is y equals 9 divided by 3 is what we did too. Or once we simplify this, we get the line y equals 3. And this is how the graph of the rational function behaves at y equals 3. All right, so both ends of the graph get closer to the line y equals 3 as x increases, and on this side as x decreases as well. A second example of finding the horizontal asymptote using a different rule here. The function given to us is g of x equals 9x divided by 3x squared plus 1. Again, same process. Start by looking at the leading exponent of the numerator and the denominator, and we will compare them, and we will find out where the horizontal asymptote is going to be. So n here is 1, which is the exponent of the numerator, and m is 2 in the denominator. So we see n is less than m, right? 1 is less than 2. So it's the x-axis or the line y equal to 0 is going to be the horizontal asymptote of this function. All right. So the degree of the numerator is 1, is less than the degree of the denominator, which is 2, right? Thus, the graph of G has the x-axis as a horizontal asymptote, which is y equal to 0. The equation of the x-axis is y equal to 0. And this is the behavior of the graph of that rational function at y equal to 0 at the x-axis. So we see that as x increases, the graph is approaching the x-axis, is getting closer to the x-axis, and on the other end, as x decreases, the graph on its left end is also approaching the x-axis. Here's a third example applying the rule where n is greater than m. So it says find the horizontal asymptote if any of the graph of the rational function h of x equals 9x cubed divided by 3x squared plus 1. Again, we look at n, which is the exponent of the leading term. N equals 3 in the numerator, and in the denominator, denoted by m, the leading exponent is a 2. Clearly, n is greater than m, 3 being greater than 2, right? N greater than m. What does the rule say? It says that in this case, it will have no horizontal asymptote. No horizontal asymptote. And that's what the solution is, right? And in the next slide, we'll look at the graph of that. The degree of the numerator 3 is greater than the degree of the denominator 2. Thus, the graph of h has no horizontal asymptote. So as you can see in this graph, there are no horizontal asymptotes. This graph is continuous, okay, and it does not have any horizontal asymptotes as such. We'll now talk about basic reciprocal functions. So what do we understand by reciprocals? In a reciprocal number, what was in the numerator goes to the denominator, and what was in the denominator goes to the numerator, right? So the reciprocal of 2 is 1/2, right? Because the number 2 has a denominator of 1. So when we take the reciprocal of 2 over 1, we flip the numerator and the denominator and we get 1/2. That's what reciprocal means. Likewise, the reciprocal of x is x has a denominator of 1. So the reciprocal of x over 1 is going to be 1 over x. So that's why they call this a reciprocal function. The reciprocal of x squared is 1 over x squared. Okay, so that's an explanation or a review of what reciprocal functions mean. Now here they have talked about the symmetry and also whether a reciprocal function is odd or even, or what happens in an odd reciprocal function versus an even reciprocal function. Now, for odd functions, we learned before, for odd functions, f of negative x is equal to negative f of x. Now, I'm not talking about reciprocal functions at this point. I'm just think about regular functions. In any regular functions which are not reciprocals, for example, just for y equals x case, an odd function would be if we replace the x with a negative x. That means here This point here has 1, 1 as its coordinates. If we replace the 1, the x value, with a negative x value, that means if we replace this 1 with negative 1, then the y value, the corresponding y value, is also going to become negative. So this point would become negative 1, comma negative 1. This point up here, which now has the coordinates half comma 2, is going to become negative half comma negative 2. That's what makes it an odd function, and an odd function will have symmetry about the origin, across the origin. All right, it's going to be a mirror image of the graph across the origin. It has an origin symmetry. What happens in a reciprocal function? In a reciprocal function, remember the numerator and the denominator flip, right? So it's not just that the negative half, I'm just trying to pull my pen up here. It's not that, let's say we have 1, 1, right? And in an odd function, what was going to happen? This negative 1, if we replaced negative 1 with, actually, I'm going to I'm going to use a different example, because since both the values are the same, both the coordinates are the same, it's not going to be a good example to explain. All right, so I'm going to use another example here. I'm going to use 1/2. All right, this first point here, I'm going to use 1/2 comma 2. So this point here has coordinates 1/2 comma 2. What the odd function rule says is, if we replace the 1/2, if we replace the 1/2 with a negative half, then the y value is also going to become negative 2. Okay, so if it says here f of negative x is equal to negative f of x. So that means if we replace the x value with its negative counterpart, then the y value would also become a negative. All right. Now, what happens in reciprocal functions where we have, let's say, 1 divided by x? Remember, in reciprocal functions, the numerator and the denominators flip, right? What was in the numerator goes to the denominator in the reciprocal function. What was in the denominator of the original function goes to the numerator. So what's going to happen is, instead of having negative half comma negative 2, we are going to end up with negative 2 comma negative half. All right, it's going to flip. Likewise, let's take another point, 2 comma half. All right, so here we have 2 comma half. When we replace the 2 with a negative, with its negative, it's not only going to become negative half, it's going to have the point negative half comma negative 2. That's what original symmetry means, symmetry across origin. So let's look at the points here. This was half comma 2. This point had half comma 2. For an odd function which has symmetry about the origin, it becomes negative half comma negative 2. All right. 1 comma 1 becomes negative 1 comma negative 1. 2 comma half becomes negative 2 comma negative half, right? That's origin symmetry. Let's look at the graph on the right hand side, which has a function 1 divided by x squared. again, same thing here. We have the graph half comma 4. I'm just looking at the graph on the right hand side in the first quadrant. This point here has half comma 4. Then we have 1 comma 1 and 2 comma 1/4, 2 comma 1/4. If we replace 1/2 with negative 1/2 in an even function, the y value doesn't change. When we replace x with negative x, then the y value still remains unchanged, f of x. And that's what we see here. When we replaced half with its negative counterpart, negative half, the y value didn't change. It was still positive 4. 1 comma 1, we replaced 1 with negative 1. The y value still remained positive 1. And likewise, when we replaced 2 with a negative 2, the y value remained positive 1/4. Okay, so even functions and symmetry occurs on rational expressions, reciprocal functions, the same way as with any other function. We are now going to talk about transformations to graph of a rational function. Now, when we had learnt about transformation in a previous chapter, we said that we started with the basic graph of each type of function. So maybe y equals x, or y equals x squared, or y equals x cubed, or y equals absolute value of x. We started with the basic function, and then we used the rules of the transformation to determine how the graph it was going to transform, whether it's going to have a vertical shift or a horizontal shift, or a vertical stretching or a shrinking, or horizontal stretching or shrinking. So we're going to do the same here, but our basic function for a rational function is f of x equals 1 divided by x. That's going to be our basic graph, and then we are going to use the rules of transformation on the basic graph to determine how this is going to shift or shrink or stretch and so on. All right, now I'm going to write here the basic form of not the basic form, sorry. I'm going to write here the form of transformations that we learned to determine how the graph is going to transform. So we start with A, and then we have c times x minus h plus k. All right. And let's just run over what each of these variables here mean, or constants, not variables, constants here mean. A determines vertical stretching, shrinking, as well as its sign determines reflection. C determines horizontal stretching or shrinking. H determines horizontal shifting, whether it's going to shift to the how many units to the left or how many units to the right. And K determines vertical vertical shifting. That means whether it's going to shift up or down along the y-axis. All right, but let's go into first the basic graph. The basic graph of a rational function 1 over x has the y-axis as its vertical asymptote and the x-axis as its horizontal asymptote. And the graph, as we approach the asymptote, as we approach x equal to 0 from the right-hand side, the graph rises indefinitely to infinity. The function increases without bounds, and as far as the horizontal asymptote is concerned, which is y equal to 0 line, the graph heads towards the line y equal to 0 for increasing x values. As x values increase, the graph heads towards y equal to 0. Okay. On this third quadrant, this part of the graph, what happens is, as we approach the vertical asymptote, from the left, the graph heads towards negative infinity. So let me write it down the way we learned it. Okay, as far as the vertical asymptote is concerned, as x approaches 0 from the negative side for this one, as we approach 0 from the negative side, f of x approaches negative infinity, correct? That's what it is. As we approach 0, as x approaches 0 from the negative side, f of x approaches negative infinity. And for here, it's as x approaches 0 from the positive side, f of x approaches positive infinity. Okay. As far as the horizontal asymptote is concerned for this part of the graph, as x values decrease, the graph heads towards the horizontal asymptote, which is y equal to 0. So that's the behavior of the graph 1 over x, which has vertical asymptotes as x equal to 0 and a horizontal asymptote at y equal to 0.
Let's go through this example on transformations and actually draw the graph. So the basic function was f of x equals 1 divided by x, right? That's the basic rational function. This here, 1 divided by x plus 2 minus 1, is the transformed form of 1 divided by x, all right? So we have the 1 divided by x in this function, but then there is a plus 2 with the x, and then there's minus 1 from the entire 1 divided by x plus 2. So if we go back to our transformation form, it's a times, actually it's a times c times x. So let me write the complete form here. So a times c times x minus h plus k. Okay, so let me explain what each of these constants mean as far as transformation is concerned. A means A suggests vertical shrinking or stretching. All right. So A determines vertical stretching and shrinking, and the sign of A determines reflection. All right. C determines horizontal stretching and shrinking. It's a multiplicative of x. H determines the horizontal shifting, whether the graph is going to shift to the left or right from its original graph, from the basic graph. And K suggests vertical shifting up or down, whether the graph is going to move up or whether it's going to move down the y-axis, along the y-axis. So let's pick up our values from here and see what are applicable, which of these are applicable in the function that's given to us. So A here is 1. If we don't see any value over here outside of the function, then that means a is 1, all right? C, there's no C. We don't see the x multiplied by any value, so this is not applicable. We have x plus 2. So there is the x minus h horizontal transformation involved here. And then there is k, which is this minus 1, right? That means vertical shifting. So this graph will involve horizontal shifting and vertical shifting. There's no stretching or shrinking or reflections involved. All right, so now let's find out the values of h and k. So I'm going to write x plus 2 in the x minus h form. So when I do that, all right, so let's take this. All right, so it's going to be 1, all right, divided by, if I put the x plus 2 in the x minus h form, it's going to be x minus, all right, the form is x minus h. There's a minus in the form, so you have to make that minus visible to put it in the form. So if we pull out the minus from the plus, we are left with minus 2, because once we multiply the two minuses, it will become plus, and we'll get back the x plus 2. All right, so x minus minus 2, and that is going to be the value of h, and there is plus. All right, so we have a plus in the form, there's a plus. So we are going to show the plus, and what remains? Minus 1. Minus 1, right? And that's the value of k. So we have h equals -2, which means it's horizontally shifting to the left 2 units. So shifts left by 2 units, all right, 2 units. 2 units to the left is the horizontal shifting, and k is -1, which means it's going to slide down 2 units. When k is negative, it's a downward shift, so it shifts down 1 unit along the y-axis. Shifts down vertically 1 unit. Okay, so here let's look at the graph here. The basic function has this black curve here. This black graph is that of the basic function 1 divided by x. Okay, these is f of x equals 1 divided by x. Now, what happens is, in 1 divided by x, all right, when x equals 1, all right, when x equals 1, y is also going to be equal to 1, right? So if we plug in 1, so let's say we have the function f of x equals 1 divided by x. I want to find an easy point on this curve here, on this curve. Now if I plug in 1 into x, then y is also going to be 1. 1 divided by 1 is 1, so 1 comma 1. So 1 comma 1 is going to be a point over here, right? So if this is, if this is 2, let's make 1 here, and this is 1. So here is 1 comma 1. All right, 1 comma 1. All right, so when we make the transformations, when we draw this transformed graph, if we have a point located, it'll be easier to shift that point by so many units, all right, whether to the left or to the right. We'll use this as our point of reference, so to speak, for the graph. So we saw that the vertical asymptote, all right, is going to be over here. Remember, for the vertical asymptote, it's going to be at -2. How do I know? I take the x plus 2, make it equal to 0, and solve for x, right? So the vertical asymptote, which was initially x equal to 0, is now going to be x equals to -2, because h suggests it's going to shift left by 2 units. So what was at x equal to 0 will now be at x equals -2. So that's the first thing. We have to shift the vertical asymptote first. And then there is a horizontal asymptote as well. All right. So the horizontal asymptote is at y equal to 0. That is going to shift down 1 unit. All right. It's going to shift down 1 unit. So we first draw the graph along the vertical asymptote. All right. The horizontal asymptote is still at y equal to 0, and we draw the graphs here. Okay. So this whole thing shifts to the left. So 1 comma 1, what was 1 comma 1? You subtract 2 from, all right, you subtract 2 from the x coordinate of 1, and that's 1 minus 2 is going to be -1, right? So we have this point shifted to -1 comma 1, and it'll be easier if you have one point. It'll be easier for you to kind of draw the graph. All right, now in the previous slide we had just shown the vertical shift of the function, all right, of the transformed function. The vertical asymptote shifted 2 units to the left from where it was, and therefore the points on the original graph also had their x values shifted 2 units to the left. So we had this point here. I think we identified an easy point on the basic graph, and we said it's 1 comma 1, right? This point here is 1 comma 1. When we shift it 2 units to the left, the x value is going to be -1 comma 1. All right, so this point here shifted over here, right? Let's say this is -1. Okay, it shifted. It shifted 2 units to the left. Now, there was also vertical shifting involved, right? There was also vertical shifting involved. That means the graph was sliding down 1 unit. All right, remember the form was, well, the function was y divided by x plus 2 minus 1, right? So we took care of the x plus 2, which is the horizontal shift, by sliding the vertical asymptote 2 units to the left, and therefore the graph, the original graph, also slided over 2 units to the left. All the x coordinates shifted 2 units to the left. Now we have to take into consideration the vertical shift, which is 1 unit down. This is k was -1, so it has to slide the horizontal asymptote first has to slide 1 unit down. And what will that happen? What will that result in? It's going to change the y values. All right, vertical shifting means the y values are changing. We are moving along the y-axis, so the y values will change by 1. So you have to, because it's 1 unit down, you have to subtract 1. So the original point here had 1 comma 1. When we shifted it to the left, the x coordinate became -1. When we shifted down, the y coordinates also need to be subtracted. How many units? 1 unit. So this one will become a 0. All right, 1 minus 1 will be a 0. So the point is, all right, so this point is not only going to shift to the left, but also shift 1 unit down. All right. It's going to be at -1, 0, -1, 0. The same thing for this also. All right. So we have to therefore draw this part of the graph of the rational function, and the points on this graph are also going to run along the new asymptotes, and the x and y coordinates are going to change. The x coordinates are going to uh, have 2 subtracted from it, and the y coordinates are going to have 1 subtracted from it. All right. Now let's come up with a step-by-step method of drawing the graph of a rational function. The following strategy can be used to graph a function which is in the form p of x divided by q of x, where p of x and q of x are polynomials in themselves, where p and q are polynomials with no common factors. Determine whether the graph of f has symmetry. So that's the first step. The first step is to find the symmetry in the graph. How do we do that? We substitute the x with a negative x, and we find or if we test if the y values remain the same or not. So after substituting negative x into x in the function, if the function remains the same, that means there's no change in the function from the original one, then that means it is an even function. It's a reflection across the y-axis. All right, y-axis symmetry. If we substitute if we substitute negative x into the function, and we end up with a negative y value from what it was in the original function, then it's an odd function, and its symmetry is about the origin. So that's the first step, to figure out the symmetry. The second step is find the y-intercept, if there is one, by evaluating f of 0. So y-intercept is determined by plugging in 0 for x into the function and coming up with a y value. So that will represent the y-intercept. And then number 3 is find the x-intercepts. Next step is find the x-intercepts by solving the equation p of x equal to 0. All right. Basically, we have to make the whole equation equal to 0 and solve for x. So let me just do that here. It's p of x divided by q of x equal to 0. So you have to take the entire rational function, make it equal to 0, and solve for x. Now, why do they say here just p of x equal to 0? It's because when you are solving this equation, you first have to get rid of the q of x. You have to get rid of the denominator, correct? So what do? You multiply both sides by q of x, correct? And what happens? The q of x divides, so we are left with p of x, and 0 times q of x is 0. So solving p of x divided by q of x equal to 0 is the same as making p of x equal to 0 and solving for x. All right, that's why instead of saying p of x divided by q of x equal to 0, that's how it should be stated. That's because you're actually equating the entire function to 0 and then solving for x. But because the other side is a 0, the q of x uh, is discarded after we multiply it by 0, and we end up with p of x equal to 0. So we know the first three steps of graphing a rational function is number 1, to find the symmetry of the function and therefore the graph. Number 2, find your y-intercepts. Number 3, find your x-intercepts. Now, step number 4, we have to find the location of the vertical asymptotes. And we do that by taking the denominator of the function, making it equal to 0, and solving for x. And based on the values that we find of x from the equation, those will be the locations of the vertical asymptotes. Now, we may have 0 vertical asymptotes, we may have 1 multiple asymptotes, or 2 or multiple vertical asymptotes. Number 5 is find the horizontal asymptote if there is one, using the rule for determining the horizontal asymptote of a rational function. So we had those 3 rules. In order to find the horizontal asymptote, we first have to find or look at the exponents of the leading terms in the numerator and the denominator. So the leading exponent in the numerator is n, and the leading exponent in the denominator is m. And then we do a comparison of their values. All right, so if n equals m, if they are the same, then the horizontal asymptote will be at y equals the coefficient of the leading terms. Okay, a sub n and a sub divided by a sub m. It's the ratio of the coefficients of the leading term. All right, if n is less than m, all right, then the x-axis, or y equal to 0, is our horizontal asymptote. And then finally, if n is greater than m, then it doesn't have any horizontal asymptotes, no asymptotes, HA. Let's write it there. Okay, so once we find our asymptotes, we plot at least one point between and beyond each x-intercept and vertical asymptote. So number 6 is to plot at least one point outside of the intercept and the vertical asymptote, and that point will become our reference point, especially when we go to do any transformations. And then number 7 is use the information obtained previously to graph the function between and beyond the vertical asymptotes. All right, so that's the final step. So we'll go through an example and follow these steps one by one and draw a complete graph.
Let's see how we can apply all the 7 steps that we learned before to graph the function f of x equals 3x minus 3 divided by x minus 2. All right. So the first step was to determine the symmetry. How do we do that? We substitute the x with a negative x and see if there has been any change in the f of x function. So in other words, what we do is we we just evaluate the given polynomial function, replace the x with a negative x, and we have 3 times negative x. Replace all your x's with a negative x. Minus 3 over minus x minus 2. Minus 2. And we end up with negative 3x minus 3 divided by negative x minus 2. Now, that's what we get. All right. So what we see here is that f of x, definitely it's not the same as what we started with, what the original function was. All right. So that means it's not an even function. For it to be an odd function, okay, for it to be an odd function, it should be negative of, all right, 3x minus 3 divided by x minus 2. All right. In other words, what should happen is all the signs must change in order for it to be order for it to be an odd function. And we see that didn't happen. All right. Some signs changed, but not all the terms changed their signs, correct? So that means it's neither an odd function nor an even function. So that completes the first step. So there is no symmetry as such of this function. Let's go on to the second. So step 2 is about finding the y-intercept. Now recall that at the y-intercept, the x value is always equal to 0. So all we do is we take 0 for x, all right, and plug it in wherever there's a 0 in the function and evaluate the function. So let me do it separately here, although they have worked it out, but it's not completely worked out. All right, so the function was 3x minus 3 divided by x minus 2. So I'm going to plug in 0 for wherever there is an x. So 3 times 0 minus 3 divided by 0 minus 2. 3 times 0 is 0. So we have minus 3, right? This becomes a 0, and 0 minus 2 is negative 2. Negative negative divides and becomes a positive, so we have 3 over 2. So the y-intercept is going to be at 0 comma 3 over 2. That's the y-intercept with both the coordinates, 0 comma 3 over 2. Find x-intercept. To find the x-intercept, at the x-intercept, the y value is going to be a 0. So what we do is we take the entire function 3x minus 3 divided by x minus 2 equal to, make the other side equal to 0, and solve for x. So we are solve for x when y is equal to 0. Solve for x. Now what happens is we first have to get rid of the x minus 2, correct? How do we, the denominator, how do we do that? We multiply both sides by x minus 2. All right, x minus 2. And we end up with 3x minus 3 equal to 0 times x minus 2 is 0. And now we just solve for x. So we have a simplified form, but I don't quite like the way they say that just take the just take the numerator expression and make it equal to 0, because it's an outcome of making a rational expression 0, making a rational expression equal to 0 and solving for x. It should come as step 2 in the process. All right, but what we should really do in order to find the x-intercept is take the entire function as given, make it equal to 0, all right, and then solve it, all right. Otherwise, it's kind of misleading if they just say that take the numerator expression, make it equal to. That's what we'll end up with, but we should know how we end up with, why we just work with the numerator expression instead of the entire function. All right, we do start with the entire function, make it equal to 0, and in the next step after getting rid of the denominator, we end up with 3x minus 3 equal to 0. All right, and we come up with x equals 3. They've done the solving here. So the x-intercept is at 1, 0. Okay, at the x-intercept, y is equal to 0. So we got our x-intercept, we got our y-intercept, all right, 0, 3 over 2, and now we have to find our asymptote. To find the vertical asymptotes, we just take the expression in the denominator, the polynomial in the denominator, make it equal to 0, and solve for x. Again, our function was 3x minus 3 divided by x minus 2. So to find the vertical asymptotes, just take the denominator, make it equal to 0, and we get x equals 2, and that's our vertical asymptote. Find the horizontal asymptote. We have to look at the exponents of the leading terms in the numerator and denominator. Both have 1. So n and m both are equal, right? The numerator and denominator of f have the same degree 1. So the horizontal asymptote will be 3 over 1. So 3 over 1. So y equals 3 is where the horizontal asymptote will be. Okay, so vertical asymptote x equals 2, horizontal asymptote is y equals 3. So in step 6, we can start plotting the points one by one. We start with the x-intercept, which is at 1, 0, right? So this is the x-intercept at 1, 0. Next is the y-intercept, 0, 3 by 2, 1.5. So the y-intercept, where's the y-intercept? 0, and then a point between 1 and 2, which is right here. This is the y-intercept. So y-intercept, x-intercept, and then the asymptotes. So the vertical asymptote was at x equals 2. If you look back, it was at x equals 2. So we draw this dashed line for the vertical asymptotes, and we plot some points, all right, here. Okay, we just pick some points between and beyond each x-intercept and vertical asymptote. So one point here maybe, all right, at x equals 3, another at x equals 5 over 2, and another point x equals half somewhere here. All right, so let's go to the next slide and complete this this graph. So here we plot some points. All right, we pick -1, half, 3 over 2, 5 over 2, and 3. All right, and then we evaluate the function using these x values. So when x is -1, y is 2 by plugging in -1 into this function. When it's half, it's 1. When it's 3 over 2, it's -3. When it's 5 over 2, it's 9, 3, 6. All right. The horizontal asymptote was at y equals 3. All right, so we have our vertical asymptote at x equals 2. We draw a horizontal asymptote now at y equals 3. And then using the points that we came up in the previous slide, the points between the x-intercepts and between and beyond the x-intercepts and the vertical asymptote. We found about 4 or 5 points. Using those points, we complete the graph of the rational function. So we still have the y-intercept over here, right? This is the y-intercept between 1 and 2. It was, I think, 0, 3 over 2. And here we have the x-intercept, right, at I think 1, 0, and then we have the horizontal asymptote, and then these are some of the other points that we found from our table right before this slide, and we can complete the graph by plotting those points and connecting them. All right. Now there's one more asymptote that we should know about as far as rational functions are concerned. It's called the slant asymptotes, and that happens when the degree of the numerator is 1 more than the degree of the denominator. So it says the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. In general, if we have a function p of x divided by q of x, p and q have no common factors, that still holds good, and the degree of p is 1 greater, just 1 greater. So if it is x cubed divided by x squared, it'll have a slant asymptote. If it is x to the 6th divided by x to the 5th, it'll have a slant asymptote. So n must be just 1 value greater than the exponent in the denominator, which is m. All right, so this is important. It has to be just 1 value greater, 1 number greater than the one than m. All right. So let's go into a little more about what slant asymptotes are and how they look like. Here's an example of finding the slant asymptotes of a rational function. So the rational function given to us is here 2x squared minus 5x plus 7 divided by x minus 2, and we have to find the slant asymptote. So the first thing that we have to make sure is that the degree of the numerator is 1 less than the degree of the denominator. So just look at the leading exponents. All right, here we have a 2 for the leading exponent, and in the denominator we have 1, which is 1 less than what we have in the numerator. Okay, so once we determine that condition, once we make sure that condition is met, we can go ahead and find the slant asymptote, or rather the equation of the slant asymptote. The way we do that is by dividing the numerator by the denominator. Whatever quotient we get after dividing the numerator by the denominator will be the equation of the slant asymptote. So the solution stated here says the degree of the numerator is 2, which is exactly 1 more than the degree of the denominator, which has 1, which has the leading exponent as 1, right? Now to find the equation of the slant asymptote, divide the numerator by the denominator. So they have used synthetic division to perform the division here. So we take the coefficients of the polynomial in the numerator, which are 2, -5, and 7. So that's why they have 2, -5, and 7. And over here, we divide it by the expression in the denominator. We just pick the value of c from the form x minus c. Let me write that. X minus c is the form of the denominator, right? So let's put x minus 2 in that form and pick the value of c. So c, all right, c has a value of 2. So that's why they have here 2 is what they are dividing the numerator by. So again, the process is the same. Bring down your 2 below the line and then keep multiplying. So 2 times 2, write the result below the second coefficient. So 2 times 2 is 4. We write the 4 below negative 5 and then perform an addition here. Negative 5 plus 4 is negative 1. Again, go and multiply. So 2 times negative 1 is negative 2. Write the negative 2 below the next coefficient and then add them. So 7 minus 2 is 5. So again, 5 is the remainder and the quotient will be 2x minus 1, correct? So that's what they have here, 2x minus 1, and the remainder they express as 5 divided by x minus 2. Now that we have obtained the equation of the slant asymptote line by dividing the numerator of the rational expression by the denominator and using the quotient expression as the equation, we will go ahead and see how the graph will look like. The graph of a function that has both a vertical asymptote as well as a slant asymptote. We can see that this will have this, the equation. Let me write that down first. What was the function? It was f of x equals 2x squared minus 5x plus 7 divided by x minus 2. All right, and we can see that this will have a vertical asymptote as well. How do we know that? We just take our denominator, make it equal to 0 and solve for x. That will give us the equation of the vertical asymptote. So if we just take x minus 2 equal to 0, make it equal to 0 and solve for x, then x equals 2, the line x equals 2 will be our vertical asymptote. And that's why you see a vertical asymptote at x equals 2. And the slant asymptote is y equals 2x minus 1 again. You see, this is a linear equation. You have to be able to draw the line, a dashed slant asymptote using the equation here, y equals 2x minus 1. All right. So now that we have two asymptotes, our graphs, our rational function graphs are going to have one end going along the vertical asymptote and another end of the graph going along the slant asymptote. Same here also across the x-axis here. Okay. Now we'll go into a word problem, an application problem on rational functions. So let's read through this word problem first and see what they are asking us for. A company is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000 and it will cost $400 to produce each radically innovative chair. Write the cost function C of producing X wheelchairs. So X represents the number of wheelchairs, any number of wheelchairs. Okay. What is involved in the cost? There is a fixed cost which is $500,000. All right. Whether they produce one wheelchair or 50 wheelchairs or 1,000 wheelchairs, the fixed cost will always be added to the total cost. That's the fixed cost. And there's a variable cost of $400 for each wheelchair. So the cost function is going to be C of X, X being the number of wheelchairs produced, is equal to 500,000 plus 400 times X. So $400 per wheelchair, one wheelchair, $400, three wheelchairs, 3 times 400. So the cost is going to increase by $400 for each wheelchair that they produce, and there is going to be a fixed cost of $500,000. All right, so that is the first part of the question. The second part of the question says write the average cost function C with a dash above it, so C dash, which means average cost, all right, of producing X wheelchairs is 500,000 plus 400 times X divided by X, all right? So the way we find average is you add up all the numbers, all right, and then divide it by the total number, a total amount of numbers that we have, right? So here, because they are asking us to find the average cost and not just the cost, but the average cost, we have to divide it by the number of wheelchairs, total number of wheelchairs produced. So the average cost equation is going to look like 500,000 plus 400 times X divided by X. So now we have a rational function. Previously, in the previous part, when they just asked us to find the cost and not the average cost, it was a linear function. It was just C of X equals 500,000 plus 400 times X. Once we wanted the average cost function, we had to divide it by X and it became a rational function. Now, part 3 of the question says, find and interpret the average cost of 1,000, all right, C dash or C bar of 1,000. So all we have to do in this case is take the equation of the average cost function and substitute 1,000 into X and evaluate the function. So average cost, which is C bar or C dash, C bar is the common way to read this. C bar of 1,000, just plug in 1,000 wherever there is an X. So 500,000 plus 400 times 1,000 divided by 1,000 equals 900 when we complete this evaluation. So the average cost per wheelchair of producing 1,000 wheelchairs per month is $900. So that's the average cost, all right? So part 3 said find the average cost of 1,000 chairs. Now it says find the average cost of 10,000 chairs. So again, this time we have to plug in 10,000 for wherever there's an X into the average cost function, and we come up with $450. So when we increase the number of chairs, what happened was the price came down. The average price of a chair, of each chair, came down. When it was 1,000, when we produced 1,000 chairs, it was $900 average cost per chair per month. When we increased it to 10,000, it became $450 per chair per month. All right. Let's look at. Now we want to calculate the cost, average cost of 100,000 chairs. All right. So same process, just substitute 100,000 wherever there's an X and perform the evaluation. It's 405. So we see that the average cost is coming down as we increase our production naturally, because the 500,000 is now getting distributed over 100,000 shares. All right. So therefore, the average cost per wheelchair of producing 100,000 wheelchairs per month is 405. Now part 6 of the question says find the horizontal asymptote for the average cost function. So we have to find the equation of the horizontal asymptote from this function given here. All right. Now recall that there are rules of finding the horizontal asymptote using the exponents of the leading terms of a given function. Okay, so we have to identify the leading exponents, right? However, first check if the polynomials in the numerator and the denominator are arranged properly in order of their exponents. Here we see we have 500,000 plus 400x. This is not properly arranged. So as a first exercise, I'm going to rewrite the function as 400x has to come first as the first term. That's the leading term here. And then 500,000 divided by x. So now that we have arranged it, there's nothing to arrange in the denominator because there's only one term in it. We can identify now our n and our m's and then do a comparison, right? So what is n? N being the exponent, leading exponent in the numerator is 1. And the leading exponent in the denominator is also 1. So we see that n is equal to m, and when that happens, that means the horizontal asymptote equation is formed using the coefficients of the leading term. We create a ratio using the coefficients of the leading term. So the coefficient in the numerator is 400. So we'll have that, and the coefficient in the denominator is 1, so 400 divided by 1, so y is equal to 400 is the line of the horizontal asymptote. Now, what was the purpose of finding the horizontal asymptote in context of the question? Remember that in the past exercises, in the previous parts, we saw that when the production was for 1,000 chairs, the average cost was $900 per chair. When we increased it to 10,000 chairs, the cost dropped. The average cost was reduced to $450 per chair. When the production was further increased to 100,000 chairs, the average cost dropped to, I think, $405. Now, if we keep increasing the number of chairs produced, will there be a point where the cost will become $0? No, right? That's what the horizontal asymptote is saying, is telling us that at y equals $400 is where the cost is going to even out. All right, so even if you produce 1,000,000 chairs, the average cost is going to stay around $400. It will not go less than $400. So that's the purpose that the horizontal asymptote is serving. It's telling us that the average cost is going to even out at $400 for no matter how many chairs you produce after a certain point. So the final question is, describe what this represents, meaning what this horizontal asymptote represents for the company, given that the horizontal asymptote for this function is y equals 400. Just as I said in the previous slide, that as the number of wheelchairs or as the production of the number of wheelchairs is increased, the cost per wheelchair will approach $400, but it will not go below that number.